Section 5.4, mutually exclusive events. So we learned about the concept of mutually exclusive events in last chapter, in chapter 4. And the best way to describe a mutually exclusive event is to look at a Venn diagram. So here's a Venn diagram. Let's say this is of even numbers and odd numbers. We have all the even numbers, all the odds, and then of course we have the number 0, which doesn't. That's too bad. That odd and 0 looks the same, which is in neither. So the idea is there's no numbers that are both even and odd. They are mutually exclusive. Another example we did is cats and dogs. So there were some qualities of dogs, such as they go for walks. Cats, let's say, what does a cat do that a dog doesn't? Scratches things. Okay, but then there's also some things in common. They both keep you company. So these are not mutually exclusive. They have things or elements that are in common. So when we look at a mutually exclusive event in probability, we have to treat it in a certain way. It's actually better, a little easier than events that are not exclusive. So let's go through a couple examples. So here we have Carlos. He drew a single card from a standard deck of 52 playing cards. What's the probability that the card he drew is either an 8 or a black card? So here we have all our black cards, and here we have all our 8s. So it's easy to see from this diagram that they are not mutually exclusive. There are 8s that are black, and there are black cards that are 8. So looking at probability, all the ways to draw a single card is there's 52 ways to draw a single card. Of that, there's 13 and 13, 14, 15. No, 13 and 13, 26, 27, 28. Ooh, it's the morning. Okay, so there's 28 out of 52. And then we can further go on and simplify that. So we said, the way they did is they said there's 4 8s and 26 blacks, but then they subtracted the 2 that were repeated. And they also got 28, they reduced it to 7 13ths. They drew a diagram. Here's all the 8s. See, there's 4 of them. Here's all the blacks. There's 26, but 2 of them are common, and there's 24 that are neither. Okay, so that was not mutually exclusive. Now we're probably going to look at an example that is mutually exclusive. So here we have Janek and Violetta are playing a board game. To move on this turn, Janek must roll either doubles or a sum of 7 with the 2 standard dice. What's the probability that he will move? So we either need doubles. So here we have a double, a 2 and a 2, a 1 and a 1, a 2 and a 2, a 3 and a 3, 4 and a 4, 5 and a 5, 6 and a 6. And then let's also look at all the ways he can get 7. Well, he can have a 6 and a 1, he can have a 5 and a 2, 4 and a 3, 3 and a 4. These are all the ways he can get 7. So these are all the ways he can get that desirable outcome of either having a sum of 7 or a double. So in total, all the different ways he can roll a dice, it looks like it's 6 times 6, there's 36. Oh, first of all, it says circle doubles. Well, we did that. Shade, well, we just wrote 7, okay? So we've done that. I think on the next page they have it all filled out for us. Here's all the circles and shades. Now it says sum the probabilities of the 2 events in part. Oh, we said, did it say probability? Circle and shade. Oh, determine the probability of throwing doubles. Sorry. So we have a 1, 2, 3, 4, 5, 6 in 36 chances of getting doubles. So we could also say that's 1/6. We could reduce that. And there's 6 ways to get a 7 out of 36. So we get 1/6. Okay, if we added those two things together, if we sum them, 1/6 and 1/6 is 2/6, which is a 1 and 3. Use your outcomes to determine the probability that he will roll doubles or roll a sum. How does this probability relate? Okay, so if I can do this or that, so I have 6 and 6, I have 12/36. Well, 12/36 is 1/3 when you reduce it. So it seems like we can say the probability of A or B is equal to the probability of A plus the probability of B if mutually exclusive, because there's nothing in common. So that's pretty powerful. That's kind of going to get us where we need to go. So we said the values are the same. Interesting. Illustrate the sample space in a Venn diagram. So here's my Venn diagram, and I bet you all the answers are down there. Okay. Okay, so in this Venn diagram, We have all our doubles. We have all our 7s, and then we have everything else. Okay, so in doubles we had 6 of them. We had 6 of them here, and we had, was that 24 items? I bet. 1, 2, 3, 4 times 6. Yep, 24. So there's our diagram. Are these events mutually exclusive? Totally. Look at that. How does your Venn diagram show this? There's nothing in common. How does your outcome table show this? There's nothing that's both circled and shaded in. Okay. Determine probability of throwing doubles in union using your Venn diagram. Okay, so union. So we have 6 and 6. That is 12. Oh, I made a mistake here. This should have been union. Whoops. Miss Canelon. Or things like that, not and. Okay. Sorry, it should have been union. Okay. So determine the probability using your Venn diagram is equal to 12/36 or 1/3. Okay. Given that A and B are mutually exclusive, write a formula that you could determine. So the probability of A or B equals the probability of A plus the probability of B. Suppose that he has to roll either doubles or a sum of 6. Could you use the formula wrote in part 1? Well, is there any ways are doubles and a sum of 6? Oh, look, this is not mutually exclusive because this is both a double and a sum of 6. So we could not use that formula. We would have to subtract 1 because there's 1 overlap. Okay? So I think I have another example to show here. Jamie claims that the probability of A union B is equal to probability of A plus probability of B, where they represent mutually. Is she correct? Explain. Okay. So if A and B represent mutually exclusive events, their set of favorable outcomes are disjoint. That is, they have no common elements. So the probability of A union B is going to be the number of A union B divided by the number in the whole set. So that is equal to the number of A plus the number of B, everything in here and everything in here over that. Well, you can break that up. If I have 1 plus 1 over 2, I can write that as 1/2 plus 1/2, right? Those are both just 1. This is 2 over 2, and that works out to 1/2 and 1/2 is 1. Okay, those are the same things. I can break that up. Well, the number of A over the number of U is just the probability of A. That's what probability is. And this is the probability of B, so they have proved it. That's kind of an interesting abstract proof. Okay, key ideas. You can represent favorable outcomes of 2 mutually exclusive events. So first of all, you have to determine that they're mutually exclusive, nothing in common. A and B is 2 disjoint, nothing in common sets. You can represent the probability that either A or B will occur by probability of A or B, A union B, is equal to the probability of A plus the probability of B. Okay? So again, there can be no common elements. You can represent the favorable outcome of 2 non-mutually exclusive events as 2 intersecting sets. You can represent the probability that either A or B will occur by this formula. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of its intersection. So you have to look at its intersection. Alternatively, you can say the probability of A union B is equal to the probability of A given B plus the probability of B given A plus the probability of A intersect B. When 2 events are mutually exclusive, both formulas are equivalent since this is 0, which results in the probability of that being 0. Because if there's nothing in, there's no outcomes there, then there's the probability of that is 0. So this is the principle of inclusion and exclusion. That's what this was, right? Which is used to count the elements in the union of the 2 sets to determine the probability of non-mutually exclusive events. So really, when you start probability questions, you have to ask yourself, is this mutually exclusive or not? Mutually exclusive, use this. Non-mutually exclusive, use that. So if there's anything in common between this and that, if I'm the probability of A or B, okay, is there anything in common? That's the first question you have to ask yourself.